Light is one of the most fundamental phenomena in our universe, yet it is also one of the most mysterious. At first glance, it seems simple, a stream of brightness that illuminates the world around us, but when we examine it closely, light reveals the deepest secrets of reality. Unlike ordinary objects that can be pushed, pulled, or accelerated, light behaves according to laws that defy our everyday intuition. Its most astonishing property is its constant speed. In a vacuum, light always travels at exactly 299,792,458 meters per second. This number is not just a measurement. It is a boundary that shapes the very structure of the cosmos. Unlike sound, which travels faster through steel than through air, or a car that can speed up or slow down at will, light maintains its velocity under all circumstances. No matter how fast an observer moves toward or away from a beam of light, they will always measure the same speed. This consistency is not a trivial curiosity. It is a cornerstone of modern physics, a clue that the universe is governed by rules far stranger and more elegant than our everyday experience might suggest. The constancy of light's speed was first brought into focus through experiments that sought to detect how light moved through the so-called luminiferous ether, a hypothetical medium that was once believed to carry light waves, much like air carries sound. In the late 19th century, the Michelson-Morley experiment attempted to measure differences in the speed of light as Earth moved through this ether. The result was shocking. No difference could be detected. Light's speed appeared completely independent of the motion of the observer or the source. This unexpected outcome forced physicists to reconsider the nature of space and time itself. The implication was profound. If the speed of light is fixed, then space and time cannot be absolute. They must adjust in ways that preserve light's velocity. Suddenly, light was not merely something that travels. It became a guide, revealing the architecture of reality itself. But why does the speed of light matter so much? To understand this, it's important to recognize that light is more than just a visible phenomenon. It is electromagnetic radiation, a vibration of electric and magnetic fields that can carry energy, information, and momentum across vast distances. Photons, the particles of light, are massless, which allows them to travel at this ultimate speed limit. Unlike anything with mass, they require no energy to maintain motion. When we think of moving objects, cars, rockets, or even particles, they all require energy to accelerate. As they approach the speed of light, the energy required grows exponentially. In contrast, photons travel effortlessly at this universal pace, illustrating the intimate link between light and the fundamental principles of energy, momentum, and the very fabric of space-time. Light also acts as a messenger, transmitting information across the universe. When we observe distant stars, we are essentially looking back in time, because the light reaching us has traveled millions or even billions of years to arrive. This is not merely poetic. It is a physical reality dictated by the speed of light. The cosmos communicates through these photons, and the finite speed of light defines the maximum rate at which cause and effect can propagate. In other words, the speed of light determines the ultimate tempo of the universe. Nothing can transmit information faster than this rate without violating the fundamental structure of reality. Furthermore, light's behavior is both particle-like and wave-like, a duality that challenges classical intuition. As waves, light exhibits interference and diffraction, creating patterns that seem almost magical. As particles, photons interact with matter in discrete packets, transferring energy in quantized amounts. This duality is not a contradiction, but a reflection of the deeper truth about nature. The universe does not conform to simple, human, friendly rules. Light embodies the complexity and subtlety of reality. Its speed is not just a property of the photons themselves, but a manifestation of the deep symmetries and constraints that govern all physical processes. In practical terms, understanding the speed of light has reshaped technology and science. From GPS satellites that require relativistic corrections to function accurately, to fiber optic communications that transmit data at near light speeds, the finite velocity of light defines the limits and possibilities of modern civilization. Even in fundamental physics, the speed of light serves as the boundary condition for the equations that describe the universe. From Maxwell's equations of electromagnetism to Einstein's field equations of general relativity, it is both a ruler and a law, a constant against which the behavior of matter and energy is measured. Ultimately, the constancy and ultimate speed of light are not arbitrary features of our universe. They are deeply woven into its structure. Light teaches us that the cosmos has limits, but also profound elegance. It is through light that we see, communicate, and understand the universe, and it is through the understanding of light that we come to appreciate the astonishing precision and subtlety of reality. Its speed is not just a number, it is a revelation, a cosmic speedometer that defines the very rhythm of existence. The discovery that nothing can exceed the speed of light didn't come from guesswork. It emerged from one of the most revolutionary ideas in physics, Albert Einstein's theory of special relativity. Before Einstein, scientists thought of space and time as separate, absolute entities. Time ticked the same everywhere, and distances remained fixed, no matter who was observing them. The universe was a predictable stage, with events unfolding like clockwork. But Einstein shattered this notion. He realized that if the speed of light is constant for all observers, regardless of their motion, then our understanding of space and time must be fundamentally flawed. Suddenly, time could slow down, distances could shrink, and mass could increase, all depending on how fast an object moved relative to the speed of light. The implications are profound. As an object accelerates closer to the speed of light, it does not just move faster. It begins to experience reality differently. Clocks aboard a fast, moving spacecraft tick slower relative to clocks on Earth. A journey to a distant star that seems to take decades for people on Earth might feel like only a few years for those on the ship. This phenomenon, known as time dilation, is not science fiction. It has been measured repeatedly. Particles in accelerators decay more slowly when traveling near light speed, and atomic clocks on jets or satellites exhibit measurable differences compared to their stationary counterparts. The universe is flexible in its most fundamental dimensions, and the speed of light is the thread that holds this flexibility together. The idea of mass increasing with speed adds another layer to the cosmic speed limit. As an object moves faster, its relativistic mass grows, meaning it becomes harder to accelerate further. The faster you go, the more energy you must expend to increase speed. At everyday velocities, this effect is negligible, which is why Newton's laws still work perfectly for cars, airplanes, and planets. But as you approach light speed, the required energy skyrockets, approaching infinity. In other words, no amount of fuel or force could ever push a massive object to light speed. The universe itself imposes a strict limit, and it is one that cannot be bypassed. Einstein's insight also reshaped our understanding of energy. His famous equation, E equals mc2, reveals that mass and energy are interchangeable. Accelerating an object to extreme speeds doesn't just increase its motion. It fundamentally increases its energy, effectively making it heavier in a relativistic sense. This deep connection between energy, mass, and speed is what enforces the cosmic speed limit. It's not just a rule about photons or particles. It's a principle woven into the very equations that describe the universe. Attempting to exceed light speed would require infinite energy, an impossible demand that ensures the limit is absolute. The speed of light also acts as a boundary for causality, the relationship between cause and effect. If information or matter could travel faster than light, the sequence of events could reverse depending on the observer's frame of reference. A message sent into the future could arrive in the past, creating paradoxes where causes follow their effects. Special relativity ensures that the universe preserves a consistent order of events, maintaining the integrity of cause and effect. Light speed is not arbitrary. It is the safeguard that prevents the cosmos from collapsing into logical chaos. Einstein's ideas extend beyond theory into practical applications that touch our daily lives. The Global Positioning System, or GPS, relies on satellites moving at high speeds relative to the Earth's surface. Their clocks experience slight time dilation, and if engineers did not account for this relativistic effect, navigation errors would accumulate at an alarming rate. Similarly, particle accelerators, which propel subatomic particles near light speed, must carefully calculate relativistic mass increases to control collisions accurately. Even the electromagnetic signals that carry information through fiber optic cables obey the same cosmic speed limit. These are not abstract concepts. They are rules that govern technology, engineering, and the very structure of our modern civilization. Einstein's revelation also challenges our imagination in profound ways. It reshapes what we can hope to achieve in space travel and interstellar communication. A journey to the nearest star, Proxima Centauri, is 4.2 light-years away. Even at near light speed, it would take years for travelers to reach it, and decades for messages to travel back and forth. Faster than light travel, as tantalizing as it sounds in science fiction, violates these fundamental principles. The universe imposes a speed ceiling, and that ceiling is light itself. Any attempt to circumvent it would not just be technologically difficult, it would be physically impossible. In essence, the speed of light is more than a measurement. It is a cosmic law that governs motion, energy, and time. Einstein's insights show that reality is far stranger than our everyday intuition suggests. Space bends, time stretches, and mass grows, all in a delicate balance that preserves light's role as the ultimate limit. Through his theory, we begin to see that the universe is not a fixed stage, but a dynamic, interconnected web, with light speed as its ultimate regulator. Understanding this framework allows scientists to explore not only the behavior of particles and photons, but also the possibilities and constraints of the universe itself. It is a reminder that in a cosmos governed by precise rules, some limits are absolute, and light speed is the most fundamental of them all. As objects accelerate closer to the speed of light, the universe begins to resist them in ways that are both fascinating and unforgiving. The reason lies in the relationship between energy, mass, and motion, a connection that Einstein revealed through his revolutionary insights. At low speeds, pushing an object is straightforward. The faster you push, the faster it goes, with energy increasing linearly with velocity. But as velocities climb toward the cosmic speed limit, this simplicity evaporates. The faster an object moves, the more energy it demands to accelerate even a little further. What seems like a smooth, continuous increase at first quickly becomes an exponential struggle. The closer you get to light speed, the closer you approach a point where adding more energy produces only infinitesimal increases in velocity. This effect is a direct consequence of relativistic mass. When an object moves at high speeds, its mass effectively increases, meaning it resists acceleration more and more. Imagine trying to push a freight train along a track. At first, your force produces noticeable movement. But as the train grows heavier with every additional pound you imagine, your energy barely nudges it forward. In the same way, any massive object approaching light speed becomes increasingly heavy. From the perspective of the outside universe, to reach light speed, its relativistic mass would become infinite, and it would require infinite energy, a demand the universe simply will not allow. This is not a limitation of human technology, it is a fundamental property of reality itself. The energy required to approach light speed is not just enormous, it is mind-bending. For everyday objects like cars or rockets, the energy needed to reach a significant fraction of light speed quickly becomes astronomical. Even the fastest spacecraft humanity has ever built, traveling at tens of kilometers per second, achieves only a tiny fraction of light speed. The exponential energy growth means that doubling your speed near the cosmic limit is not just difficult, it becomes essentially impossible. Every additional meter per second of velocity demands far more fuel, far more thrust, and far more energy than seems reasonable, quickly exceeding the total energy contained on Earth or even within our solar system. The universe enforces a strict penalty for approaching the ultimate speed limit. Photons, the particles of light, are unique because they are massless. They travel effortlessly at light speed precisely because they carry no rest mass. For anything with mass, the situation is entirely different. As the energy invested in acceleration increases, the velocity gains diminish, creating a natural ceiling. This cosmic speed trap ensures that the speed of light is not merely a suggestion, but an unbreakable boundary. Even if we could construct a rocket powered by exotic energy sources or tap the energy of entire stars, we would still encounter the same physical wall. Near, light travel demands energy that grows toward infinity. The universe itself conspires to prevent mass, bearing objects from exceeding this ultimate limit. This energy constraint has consequences beyond propulsion. It influences how we understand motion, collisions, and particle behavior. In particle accelerators, scientists routinely accelerate subatomic particles close to light speed. As their velocity increases, their kinetic energy skyrockets. Tiny adjustments in energy produce smaller and smaller changes in velocity, demonstrating the practical realities of relativistic mass. The enormous energy input required to nudge these particles ever closer to light speed also serves as a reminder that relativistic effects are not merely theoretical. They govern the behavior of matter and energy at all scales. Even the smallest adjustments demand careful calculation and immense energy expenditure. The energy cost of near-light travel also intersects with the challenges of space exploration. For humanity to journey beyond the solar system at velocities approaching light speed, the energy requirements would be staggering. Accelerating a spacecraft to even half the speed of light would demand fuel and propulsion systems beyond anything currently conceivable. Not only must we account for the energy needed to accelerate, but we must also consider the energy required to slow down upon arrival. Relativity ensures that both phases of the journey are governed by the same unyielding laws, making interstellar travel a monumental challenge. While theoretical concepts like antimatter propulsion or harnessing the energy of stars have been proposed, the fundamental principle remains: mass-bearing objects cannot bypass the enormous energy costs associated with near light speeds. This limit also provides perspective on the scale and constraints of the cosmos. The speed of light sets the maximum pace for information transfer, communication, and travel. Distances that seem manageable on Earth become colossal barriers at cosmic scales. Even if we could achieve velocities near light speed, vast distances between stars would translate into years or decades of travel time. The energy cost ensures that while the universe may appear infinite, its vastness is reinforced by the immutable relationship between mass, energy, and motion. Ultimately, the energy cost of near-light travel is more than a physical limitation. It is a profound reflection of the universe's structure. It demonstrates that motion, mass, and energy are inseparable, bound together in ways that define the limits of possibility. The cosmic speed limit is not arbitrary. It is the natural consequence of the laws that govern matter and energy. Einstein's insights reveal that as we approach light speed, the universe becomes an increasingly resistant medium, demanding energy that grows faster than imagination can handle. This realization is both humbling and awe-inspiring, showing that the cosmos has rules that cannot be bent, only understood and respected. As objects approach the speed of light, the universe begins to behave in ways that seem utterly alien to our everyday experiences. Space and time, which we usually take for granted as fixed and absolute, start to bend and warp under the influence of extreme motion. This is not science fiction or a thought experiment. It is a direct consequence of Einstein's theory of special relativity, and it has been repeatedly confirmed by experiment. At near light speeds, time itself slows down, distances contract, and the very nature of reality seems to stretch and twist. These effects, known as time dilation and length contraction, reveal a universe far stranger and more intricate than classical physics ever imagined. Time dilation occurs when a clock moving at high velocity relative to an observer ticks more slowly than a stationary clock. This phenomenon is not hypothetical. It has been observed in the laboratory and in everyday technology. For instance, atomic clocks flown aboard fast, moving airplanes or placed on satellites exhibit measurable differences compared to identical clocks on Earth. These differences are tiny at normal velocities, but become pronounced as speed increases. Imagine astronauts traveling in a spacecraft at velocities approaching light speed. While decades may pass on Earth, the travelers themselves would experience only a few years. The universe, in a sense, stretches the passage of time for those in motion, and it does so consistently, predictably, and irreversibly. Length contraction is the complementary effect to time dilation. Objects moving at speeds near light appear compressed along the direction of motion from the perspective of a stationary observer. A spaceship traveling at 90% of light speed would appear significantly shortened in the direction it is moving, though the occupants inside would not notice any difference in their own frame of reference. This counterintuitive effect ensures that the laws of physics remain consistent for all observers, regardless of their motion. Together, time dilation and length contraction demonstrate that space and time are not independent entities, but components of a single, unified fabric, spacetime. This fabric bends, stretches, and warps according to the relative motion of objects within it. These phenomena have profound implications for our understanding of causality and the structure of the universe. If time were absolute, faster motion would simply mean covering more distance in the same time. But because time dilates and space contracts at high velocities, the universe enforces a subtle and elegant consistency. No observer can witness violations of causality. Causes always precede effects, and paradoxes are avoided. This cosmic bookkeeping preserves the order of events, even in situations where intuition might suggest impossible outcomes. Light speed is not just a limit on velocity. It is the anchor that holds the sequence of events together. Experiments with subatomic particles provide some of the clearest demonstrations of these effects. Particles called muons, created by cosmic rays in the Earth's atmosphere, decay extremely quickly, normally in a fraction of a microsecond. Yet many muons reach the surface of the Earth before decaying, despite the distance being too great for their short lifetimes. This happens because, from the muon's perspective, time is dilated, and distances are contracted. The particles effectively experience less time and shorter distances than a stationary observer would measure. Such phenomena are not abstract curiosities. They are tangible evidence that the universe behaves differently at high speeds, following precise mathematical rules that were unimaginable before. Einstein, understanding time dilation and length contraction, also reshapes our expectations of space travel. Even if humanity could construct a spacecraft capable of traveling near light speed, journeys to distant stars would not only be physically demanding, but conceptually disorienting. For the travelers, only a short span of time might pass, while decades or centuries elapse for those left behind on Earth. This creates scenarios that challenge our intuitive sense of simultaneity, highlighting that the passage of time is not universal but relative. The universe itself becomes a more flexible, dynamic entity, governed by rules that defy common sense, but are rigorously consistent within the framework of relativity. These effects also extend to technology and modern physics. GPS satellites, for example, orbit the Earth at high speeds relative to the surface. Their onboard clocks experience slight time dilation, and engineers must correct for these differences to ensure accurate positioning. Particle accelerators, which propel particles close to light speed, must account for relativistic effects to predict collision outcomes precisely. The phenomena of time dilation and length contraction are not theoretical curiosities. They are essential for understanding and navigating both natural and engineered systems at high velocities. Ultimately, these effects reveal a universe far stranger and more intricate than our everyday perceptions suggest. Time is not a universal metronome, and space is not a rigid backdrop. Instead, they are flexible dimensions, intimately connected and shaped by motion. As objects approach light speed, reality itself transforms. Time stretches and contracts, distances warp, and the world becomes a place that is both familiar and alien. By studying these phenomena, we gain not only practical insights into the universe, but also a profound appreciation for its elegance. The laws of physics do not merely describe motion, they describe the very fabric of existence, revealing that the universe has boundaries and rules that are far more subtle and beautiful than any human intuition could predict. When we shift from classical physics to the quantum realm, the nature of light and motion becomes even more astonishing. Richard Feynman, one of the most brilliant and unconventional thinkers in the history of science, offered a perspective that challenges the way we intuitively imagine reality. He asked a simple yet profound question: how does a particle decide where to go? In classical mechanics, a particle follows a single, well-defined path, determined by forces acting upon it. But in the quantum world, things are far stranger. Feynman's revolutionary insight, known as the path integral formulation, proposed that a particle does not simply travel along one path. Instead, it simultaneously explores every possible path it could take, with each path contributing to the overall probability of where the particle will be observed. This radical idea opened a new window into the universe and gave us a deeper understanding of why light behaves the way it does. To understand the implications, consider a photon traveling from a distant star to Earth. In classical terms, we might imagine it moving in a straight line, unaffected by anything else. But according to Feynman, the photon doesn't commit to a single path. It explores countless possible trajectories, each with a slightly different probability amplitude. Some paths reinforce each other, increasing the likelihood of the photon arriving along a particular trajectory. Others interfere destructively, canceling out possibilities. Remarkably, when all these possibilities are summed, the outcome is identical to what we would calculate using classical optics. Yet beneath this simplicity lies a profoundly intricate reality. At the quantum level, particles are never bound to one path, and the universe constantly entertains every conceivable option before revealing a single, measurable result. This framework provides a fascinating explanation for the cosmic speed limit. Even in the quantum realm, light obeys the ultimate boundary. It cannot exceed its speed in a vacuum. The path integral formulation shows that photons explore multiple trajectories, but none of these paths allows them to break the cosmic speed limit. The probabilities conspire in such a way that the fastest permissible speed is always c, the speed of light. This isn't just a coincidence. It is a manifestation of the deep consistency of physical laws. At every level, from electrons to photons, the universe enforces the same ultimate limit, ensuring that causality, energy conservation, and the structure of spacetime remain intact. Feynman's approach makes this beautifully transparent. Even in a realm governed by probabilities, the speed of light remains inviolable. Beyond photons, Feynman's insights extend to all particles. The path integral formulation allows physicists to calculate the behavior of particles at incredibly small scales and extremely high energies, providing a window into phenomena that classical physics cannot describe. Particles sample all possible histories, and the resulting interference patterns determine the observable reality. In a sense, the universe is constantly balancing an infinity of possibilities, yet always respecting fundamental rules such as the speed limit imposed by light. This reveals a subtle but profound truth. The cosmic speed limit, it is not merely a classical artifact, it is embedded in the very probabilistic fabric of quantum mechanics. One of the most striking consequences of this perspective is how it connects relativity and quantum theory. While relativity governs the behavior of spacetime and sets absolute limits like the speed of light, quantum mechanics describes the behavior of the microscopic world with probabilities and uncertainties. Feynman's formulation bridges these domains, showing that even in a world ruled by quantum uncertainty, the speed of light remains the ultimate ceiling. Particles can explore an infinite number of paths, yet they do so in a way that is fully consistent with the relativistic structure of spacetime. It is a beautiful demonstration of the universe's internal logic. Even the most seemingly chaotic quantum processes are bound by profound and elegant constraints. Feynman's approach also challenges our intuitive notions of motion and causality. In the classical view, a particle's path is deterministic and straightforward. In the quantum view, every potential path contributes to reality simultaneously, creating a web of possibilities. Yet this web is not lawless. The probabilities encoded in the path integral ensure that particles cannot simply bypass the cosmic speed limit, that information cannot travel faster than light, and that events unfold in a causally consistent manner. The universe, it seems, enforces its own rules at every scale, from the tiniest quantum fluctuations to the motion of galaxies. The practical applications of these ideas are far-reaching. Quantum electrodynamics, the field that describes the interactions of photons and charged particles, relies heavily on Feynman's path integral methods. These calculations underpin our understanding of everything from atomic structure to particle collisions in accelerators. Even technologies such as semiconductors, lasers, and MRI machines ultimately depend on principles illuminated by Feynman's insights. But beyond their practical utility, his ideas reshape our philosophical understanding of reality. The universe is not simply a collection of objects moving in predictable paths. It is a complex, probabilistic tapestry where every potential history matters, yet the ultimate rules, such as the speed of light, remain inviolable. In essence, Feynman's contributions reveal that the cosmic speed limit, it is not a superficial boundary, but a fundamental feature of nature, woven into the fabric of probability itself. Particles explore infinite possibilities, yet every possible path respects the ultimate law of light speed. This interplay of freedom and constraint, chaos and order, is what makes the universe both astonishing and comprehensible. Through Feynman's eyes, we see that light's speed is not merely a number to measure. It is a principle, a rule embedded deeply in reality, guiding everything from the tiniest photon to the grandest structure in the cosmos. It is a limit that defines the possibilities of motion, information, and energy, and it is a limit that no ingenuity can escape. The question of why nothing can surpass the speed of light is one that has fascinated scientists, philosophers, and thinkers for over a century. On the surface, it might seem like an arbitrary limit, a number chosen by nature without deeper significance. Yet, when we examine the principles of physics, from relativity to quantum mechanics, it becomes clear that this limit is neither accidental nor optional. It is a fundamental feature of reality, woven into the very fabric of space and time. Every experiment, every calculation, and every observation reinforces the same truth. The universe has a maximum speed, and that speed is the speed of light. At the heart of this limitation lies Einstein's theory of relativity. Special relativity showed that as objects with mass accelerate toward light speed, their energy requirements increase dramatically. An object's mass effectively grows with velocity, requiring ever more energy to continue accelerating. To reach the speed of light, an object with mass would require an infinite amount of energy, which is simply impossible. This is not a technological constraint. It is a fundamental law of nature. The universe enforces this limit rigorously, ensuring that no matter how advanced our technology becomes, no object with mass can ever exceed light speed. But the implications go deeper than energy alone. Exceeding the speed of light would upend causality, the principle that causes precede effects. In our everyday experience, we observe a clear order of events. A match is struck, it ignites, and a flame appears. If information or matter could travel faster than light, this sequence could be reversed in some frames of reference. A message sent from one location could arrive before it was even sent, creating paradoxes that defy logic. Special relativity ensures that these violations do not occur. Light speed is the cosmic enforcer of temporal order, preserving the consistent sequence of events throughout the universe. Without it, reality itself would become incoherent, and the universe would lose its fundamental structure. Quantum mechanics, surprisingly, reinforces this limit as well. While Feynman's path integral formulation allows particles to explore an infinite number of possible paths, none of these paths permit faster than light travel. Even at the quantum scale, probabilities conspire to respect the universal speed limit. Photons, the carriers of electromagnetic force, travel at light speed precisely because they are massless, and all other particles are bound by the same cosmic rule. The universe, from the tiniest quark to the largest galaxy, obeys a consistent principle. No signal, particle, or influence can outpace light. This alignment between quantum mechanics and relativity is one of the most remarkable features of modern physics, demonstrating a deep and elegant harmony in nature's laws. The geometry of spacetime itself helps explain why light speed is unbreakable. In relativity, space and time are not independent. They are part of a unified, four-dimensional continuum called spacetime. Objects move along paths in this continuum, called world lines, and the speed of light acts as a boundary for these paths. The closer an object moves to light speed, the more time dilates and distances contract, keeping the object within the limits of spacetime geometry. To exceed light speed would require breaking this geometric structure, essentially tearing the fabric of reality. The universe is constructed in such a way that light speed is not just a speed limit. It is a built-in feature of the dimensions themselves. Thought experiments illustrate why exceeding light speed is fundamentally impossible. Consider a spaceship attempting to travel faster than light to reach a distant star instantaneously. From the perspective of an outside observer, the spaceship's journey would require reversing the order of events, sending information back in time, and creating paradoxes. Even hypothetical particles known as tachyons, which are theorized to always move faster than light, would violate causality and destabilize the logical structure of the universe. These inconsistencies are not minor inconveniences. They would make the very concept of cause and effect meaningless. Physics, it seems, has been constructed to prevent such contradictions, and the speed of light is the ultimate enforcer of this order. Experimental evidence further confirms this limit. Particles accelerated in high-energy colliders, such as protons in the Large Hadron Collider, can reach velocities exceedingly close to light speed. Yet no matter how much energy is applied, they never surpass this ultimate boundary. Even natural cosmic phenomena, like particles ejected from supernova or quasars, obey the same rule. Observations across the universe consistently reinforce that light speed is absolute. Attempts to circumvent it, whether through wormholes, warp drives, or hypothetical tachyons, face not just technological hurdles, but fundamental physical impossibilities. The universe appears to be structured with this speed limit as a cornerstone. This limit also has profound implications for communication and information transfer. Light speed is the ultimate rate at which information can travel. Signals, from radio waves to laser pulses, cannot propagate faster than this. This sets a fundamental limit on real-time communication across cosmic distances. Even if humans someday colonize other star systems, messages between planets or civilizations will inevitably experience delays dictated by light speed. It is a reminder that while technology can push boundaries, the universe imposes immutable constraints that govern even our most ambitious aspirations. The cosmic speed limit also connects to energy, momentum, and mass in a profound way. Energy and mass are interchangeable, as Einstein revealed in the famous equation E equals mc2. As objects accelerate, their relativistic mass increases, linking motion directly to energy requirements. This intrinsic relationship ensures that the faster something moves, the more energy is required to continue accelerating, creating a natural barrier. Unlike ordinary friction or resistance, this barrier is built into the structure of spacetime itself. The universe does not allow exceptions. The speed of light is not a suggestion, it is a law. Finally, the universality of this limit reinforces the elegance of the cosmos. From photons traversing interstellar space to subatomic particles in a laboratory, from distant galaxies moving in cosmic expansion to human-engineered spacecraft, everything obeys the same rule. The speed of light is the unifying principle that maintains order, coherence, and causality throughout the universe. It shapes the possibilities of travel, the transmission of information, and the very structure of reality. It is a boundary that is simultaneously restrictive and awe-inspiring, showing that the cosmos is both comprehensible and profoundly mysterious. In conclusion, nothing can surpass light speed because the universe is fundamentally built that way. Energy requirements, spacetime geometry, causality, quantum probabilities, and experimental evidence all converge on the same truth. Light speed is the ultimate boundary. It is a cosmic law, not a technological challenge. Attempts to exceed it are not just impractical, they are impossible within the framework of reality. By respecting this limit, we gain a deeper understanding of the universe, appreciating both its constraints and its beauty. The speed of light is the ultimate measure of what is possible, guiding motion, energy, and information throughout the cosmos, and revealing the profound logic and elegance embedded in the very structure of existence. The speed of light is not just a number. It is the ultimate governor of reality, setting limits on motion, energy, and the very flow of information across the universe. Understanding this cosmic speed limit reshapes not only our grasp of physics, but also our perspective on humanity's place in the cosmos. It defines what is possible for travel, communication, and exploration, while simultaneously offering a profound lesson about the universe's structure and the boundaries within which life and civilization operate. The speed of light is both a restriction and a guide, and its implications extend far beyond theoretical physics into practical and philosophical realms alike. One of the most immediate consequences of the light speed limit is its influence on space travel. The dream of interstellar exploration has long fascinated humanity. Science fiction often imagines ships darting between stars in days or hours, yet reality imposes far stricter constraints. Even if we could accelerate a spacecraft to velocities approaching the speed of light, vast distances in the universe ensure that journeys would still span years, decades, or even centuries. For example, the closest star system, Proxima Centauri, lies 4.2 light years away. Traveling at 99% of light speed, a journey there would take slightly over 4 years from the perspective of those aboard the spacecraft. However, decades would pass for observers back on Earth, illustrating the stark temporal consequences of high-speed travel. The universe's structure is unforgiving. Distance and time are interwoven, and the speed of light is the ultimate boundary that governs both. This limit also shapes communication across cosmic distances. Radio waves, laser signals, and other forms of electromagnetic transmission all travel at light speed. Even in a future where humanity colonizes multiple star systems, instant communication would remain impossible. Messages sent to nearby stars would take years to arrive, and replies would take equally long to return. The speed of light enforces a finite rhythm on the exchange of information, dictating the tempo of interaction across the cosmos. It establishes a universe where simultaneity is relative, and real-time communication becomes a concept bound strictly to local environments. This limitation is not a flaw. It is a fundamental characteristic of reality, and it shapes the strategies and technologies necessary for interstellar coordination. Beyond practical considerations, the light speed limit profoundly affects our understanding of causality and the interconnectedness of events. If faster than light travel or communication were possible, the sequence of cause and effect could break down. Events could appear to occur out of order, and paradoxes could arise. The universe's strict adherence to light speed prevents such inconsistencies, maintaining a coherent temporal structure. In this way, the speed limit is not merely a constraint on motion. It is a safeguard for logical consistency in the cosmos. Every process, from atomic interactions to cosmic events, respects this boundary, ensuring that the universe remains a coherent, predictable system, even amid the apparent chaos of quantum fluctuations and gravitational phenomena. The philosophical implications are equally profound. The speed of light teaches us about the limits of human ambition, illustrating that the universe is not infinitely malleable. Our technology, ingenuity, and imagination cannot bypass fundamental laws. They must operate within the boundaries established by nature. Yet this limitation is also a source of inspiration. By understanding the constraints imposed by light speed, scientists and engineers can devise creative solutions to navigate them. Concepts like relativistic travel, time dilation for long voyages, and probabilistic quantum communication are not attempts to break the speed limit. They are methods of working within it. The universe, it seems, challenges us to respect its rules while still exploring the farthest reaches of possibility. Moreover, light's speed limit shapes the very structure of our universe and the phenomena we observe. Galaxies receding at high velocities, cosmic background radiation, and the behavior of particles in accelerators all demonstrate the pervasive influence of this ultimate boundary. The speed of light governs the propagation of forces, the transfer of energy, and the coordination of events across vast distances. It defines the horizon beyond which information cannot travel, shaping our perception of the cosmos itself. The observable universe is, in a sense, framed by light speed. What we can see, know, and influence is bounded by this cosmic velocity, reminding us of both the vastness of space and the finite. Limits imposed by fundamental physics. In technological terms, respecting the speed limit, it has already transformed human civilization. Satellite communications, GPS navigation, fiber optic networks, and particle accelerators all operate within the constraints imposed by the speed of light. Engineers account for time dilation in GPS satellites to ensure accurate positioning, and scientists design particle collisions with relativistic corrections in mind. The cosmic speed limit is not just a theoretical principle. It is a practical consideration that affects the precision and reliability of the technologies on which modern life depends. By acknowledging and incorporating this boundary, humanity has harnessed the power of nature without attempting to violate it, demonstrating that profound limitations can coexist with ingenuity and progress. On a more cosmic scale, the speed of light also sets limits on our understanding of the universe's age and size. Light from the most distant galaxies takes billions of years to reach us, meaning we see these galaxies as they existed in the distant past. The finite speed of light imposes a look-back time, allowing astronomers to reconstruct the history of the cosmos while simultaneously reminding us that there are regions forever beyond our observational reach. The universe is vast, dynamic, and constrained by this immutable limit. It is a reminder that while exploration and discovery are possible, there are boundaries that define the very horizon of knowledge. Finally, the speed of light offers a philosophical lens through which to consider the nature of reality itself. It is a reminder that the universe operates according to principles that are both precise and universal, independent of human desires or imagination. While humans may dream of faster than light travel or instantaneous communication, the cosmos imposes boundaries that cannot be arbitrarily changed. Yet these boundaries are not restrictive in a negative sense. They provide structure, coherence, and a framework within which exploration, discovery, and innovation can occur. The speed of light defines the arena in which reality unfolds, guiding energy, information, and matter, and ensuring that the universe remains a comprehensible and ordered system. In conclusion, the implications of the speed of light are far-reaching, influencing travel, communication, technology, and even our understanding of time, causality, and the universe itself. It is a cosmic rule that governs the behavior of everything from subatomic particles to galaxies, shaping both the possibilities and limitations of existence. By studying and respecting this ultimate speed limit, humanity gains insight into the structure of reality, the rhythm of time, and the boundaries of exploration. The speed of light is not merely a physical constant. It is a profound principle that defines what can and cannot occur, illuminating the universe while simultaneously revealing the limits of what is possible. In recognizing these constraints, we do not diminish our aspirations. Instead, we gain a deeper appreciation for the elegance, order, and majesty of the cosmos, guided always by the ultimate speed limit that governs all motion and all possibility.